Welcome to qnawire.
So welcome to a new problem where this time we have a table, and on the table we have a block. We're going to call this block A, and then we have another block. They're connected together with a pulley that's frictionless. So we have another block. So the pulley has negligible mass. There's a second block. We're going to call that B, and B is going to drop a specific height, uh, which we'll call H. And then remember, the system is moving this way, so it has a common velocity moving that way. That's the system. There's a frictional force that's opposing the motion of the block on top of the table. The coefficient of friction, of kinetic friction, is mu k equals to 0.250. That's the coefficient of kinetic friction. The block on the table, the mass of A, happens to be 8 kilograms, and then the mass of B happens to be 6 kilograms. Remember, B also has a weight, so B is moving downwards with a weight mvg. Okay, this one has a weight mag, but it's opposed by a normal force N, which by Newton's third law of action and reaction forces happens to be equal to mag. Because the block is moving towards the right, it's moving this way, the frictional force Fr is going to be mu k times the normal, which is mu k times mag. And so, the work done by friction, remember, work in general is force times the displacement. So, if you think about Fx, so the force is mu k mag, but the distance that block A moves is also equivalent to h. So for them to have a common velocity, they have to move the same distance. And so this work done by friction is going to be mu k mag times h. It's a negative because, you see, friction is opposing the motion of this block. That's part of the work done in the system. Also, the work done by gravity, that's for this part. Remember, work is force times displacement, but then the displacement is h. The positive direction is downwards. The force itself is mvg times h. That's the work done by gravity. And then this is the work done by friction. So that's the total work done in the system. And so, using the work energy theorem, our goal is to solve for the velocity. Our goal is to solve for the velocity v. The work done by the system will be the work done by friction, or rather, I need to change that a little bit and say the work done by gravity plus. So the work done by gravity, do that. So this is the work done by gravity plus the work done by friction happens to be equivalent to the change in kinetic energy. The change in kinetic energy is final kinetic energy minus initial kinetic energy of the system This initial will be 0 because at the beginning the system is not moving. It starts from rest. So the system starts from rest. It's not moving. The work done by gravity, as you can recall, is mgh or mb. I need to change that. The work done by gravity is mbgh. The work done by friction opposes the motion, so it's negative, which is mk ma gh. That's what we have right there. So we have the work done by gravity, which is mbgh, and then the work done by the system, which is mu k ma gh, just to make sure that we know what exactly is happening in terms of h. H happens to be 1.50 meters, so don't forget that. This is equivalent to change in kinetic energy. The system has two masses, ma plus mb, and they have a combined velocity squared. Remember, the initial kinetic energy doesn't count because it's 0. In this case, we want to solve for the final velocity. So we can multiply both sides by 2. And so we have 2 mb gh minus mu k ma gh equals to ma plus mb v squared. Our target is to get the final velocity of the system. That's our goal. This one right here. We want to get the final velocity of the system. We end up dividing both sides by ma plus mb over ma plus mb. So v squared equals to 2 mb gh minus mu k ma gh all over ma plus mb. That's v squared. We're going to proceed to the next page, and just to have a glimpse of what's happening right there, we have v squared. V squared happens to be equal to, go back 2. I can pull out gh from the inside. It's a GCF, so I can pull it out. This is factorization. If I use distributive property, I can still get back the same thing I had before. So mb minus mu k ma. So mb minus mu k ma all over going back ma plus mb. And so to solve for the final, I need to get the square root of this whole thing. And like I said, it's always the best practice to keep the variables up until the end so you don't make numerical mistakes, as we call them. And so v is 2 times 9.8 meters per second squared times 1.50 meters. mb is the mass of the block going downwards, which is 6.00 kilograms. Just want to make sure that this is 6.00 kilograms. So this is kilograms, not grams. Coming back, we have minus the coefficient of kinetic friction is 0.250. That's a common number. Times ma, which is 0.8 kilograms, all over the mass of A, which happens to be 8.00 kilograms, plus 6.00 kilograms. See, the good thing about keeping all your variables up until the end is that you avoid making numerical mistakes. So just like a quick recap, there is work being done inside of the system, and that's work done by gravity and also by friction. Work done by gravity is mbgh because of the mass that's hanging, and then we subtract the work done by friction, which is negative mu k ma gh. We have that on one side. The initial kinetic energy, as you can see, this one, the initial kinetic energy happens to be 0. So we ignore that and we just keep the final kinetic energy. It's a common ma and ab v squared. So that change in kinetic energy is equal to the total work that's being done in the system, and it's going to help us solve for the final velocity. So you reorganize the problems using algebra. You can see this 1/2, multiply everything by 2. We have this 2 right here, the 2 cancels. And so we end up with MA plus MB. We divide it on both sides, as you can see. This one here cancels that. So we're left with V squared and a clean formula. This GH and GH is common. So in the next part, we can pull it out because it's the same thing. And you see that happens. It simplifies our computational process. And so we end up with a clean radical. We plug in the numbers and we get a final answer of 2.90 approximately meters per second, 2.90 meters per second. Hope you enjoyed the video. Feel free to send any questions and comments. Looking forward to responding to any questions you have, and have a wonderful day. Okay, bye.